All right. Today we're going to talk about polynomial, right? Polynomials. So before we get into the topic of polynomial, let's talk about monomial first. Poly means many, mono means single, one, right? So before we get into many, let's talk about mono, single. So monomial. Monomial means a single term. So monomial looks like this. A x to the k power. A x to the k power. So here A is constant. So what do they mean by constant? Constant simply means number. What about this x? This is variable. So x means variable, something that's varying. This exponent k, this must be an integer and it must be greater than 0, equal to 0. So integer and k has to be bigger or equal to 0. So if a term satisfies this condition right here, then we call that monomial. So what do they mean by integer? Integer simply means nice clean number, right? And it has to be greater than or equal to 0. So I guess it starts with a 0, 1, 2, 3, 4, dot, dot, dot. You get the point, right? So no 1.2, no 2/3, 1/3, none of those fraction or decimal point type of number. It's just a nice clean number, and that's what we call the integer value. So if any term satisfies this, then it's going to be a monomial. Constant simply means number, any number, right? So it could be any number, including 0, of course. All right, so let's do an example of monomial. Examples of monomial, right? Well, not really straight monomial. All right, so let's say it has to look like a x to the k, remember? Ax to the k. So one example that we can think of would be, say, 3x to the 5th power, right? We have this nice number a, which is 3. We have nice variable x, and we have this nice k, which is definitely an integer and definitely not negative. So monomial. All right. What about, say, 2x? Well, we have nice number a, which is 2. We have variable, and since we don't really see anything in place of k, we assume that there's a hidden 1. If there's 1, then we don't really say, we don't really put there. So that's also a nice clean integer, so that's a monomial term. What about, say, x to the 5th power? Well, there's no a term, right? It has to look like this. But since there's nothing, then we can assume that there's a hidden 1 as well. 1 times x to the 5th. So we have that a2. Last example, say 3. Well, we have this number a, but we don't really have x in the k power. Well, then again, we can think of this as 3x to the 0 power. What's x to the 0 power? Well, x to the 0 power is 1. So this is the same thing as 3 times 1, which is 3, which means all these examples are examples of monomial. All right. All right. Let's talk about um, examples of non-monomial. So examples of non-monomials. Okay. So what you really should be careful is this k. This k right there. If that's negative number or non-integer value, that consider as non-monomial term. That consider as non-monomial term. So, you know, 3x to the negative 4. Definitely not positive, so non-monomial. How about 2x to the negative 11? Well, negative number, out. How about x to the 1/2 power? Well, non-integer, out, right? How about 5x to the negative 1/3? Non-integer, negative, double out. So all this is going to be non-monomial terms. Non-monomial terms, right? All right. So we just quickly go back. We were trying to figure out what polynomial. Before we start talk about polynomial, we talked about monomial terms, right? Monomial terms. And monomial terms looks like this, right? Ax to the k power. A is just a constant. K is a variable. So technically, since this is, x is a variable, technically this doesn't have to be always x, right? It could be y, could be z, could be any other variable that we usually use. That k is one thing that we really have to be careful. It has to be integer and has to be greater or equal to 0, right? So examples of monomial, as you can see, is all this, and these are examples of non-monomial. All those trouble points, negative, negative, non-integer, non-integer, negative, right? All right. Now, let's talk about polynomial, the actual topic that we like to talk about, which is polynomial. Polynomials. So polynomial looks like basically this. A n x to the n power a n minus 1 x to the n minus 1 power dot 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 a to the 1 x to the 1, or if it's 1 we don't really write anything, then a to the 0. Okay, so what are all those a's? All those a's, these are number, right? All those a's is a number, basically. Any number, including 0. And these a's, the number that right in front of variable, then we can also call this coefficient, right? Coefficient. I guess it's a fancier name for those number right in front of x. Coefficient. All those x, these are variable, of course. All those variables. And all those n minus 1, all the way 1 and 0. These are, I'm talking about these numbers right here, right? All these, there's nothing here. I mean, if there's just a single terms like that, technically that means we have x to the 0 power, right? What's anything to the 0 power? Same thing as 1, right? So a0 times 1 is just the a0. So these n's exponent, of course, that's the name of those number right in front, right above these variable exponent. But this exponent has to be greater or equal to 0, and they also have to be integer. It has to be integer, right? Well, I guess at this point, student might be confused because of those an minus 1, a1 and a2. What are those? These are just simply number. Why do they use n minus 1, n minus 2, n minus 3, all the way up to a1 and a0? Well, because they're trying to say these are all different types of number, right? Don't get confused with these. These, they're talking about the exponent, right? They're talking about the polynomial. These are exponent. So all those number right above the x, that has to be non-negative integer value. Then we are fine. All those number right in front of the variable x, they are just a number. Any number. Negative, non-negative, integer, non-integer, we don't care, right? Just a number. So don't get confused with all those, this n minus 1 and an and all that. Simply that all those a's simply just means they're numbers. All right. Let's talk about examples, right? Examples of polynomial. So polynomial. Let's say, nice example would be something like this. 5x to the third plus 2x to the square minus 4x plus 7. As you can see, these are nice. It follows nice format of this typical polynomial. Let me go back to the example, right? So we have all those a's, right? All those a's, those numbers, right? Those number. I guess I can include those signs, right? Positive or negative numbers. And we have these variables, and more importantly, the exponent of variable, they are all fine looking, bigger than 0 or equal to 0, and they are all integer, which means this is going to be a polynomial. All right. So the second example, how about 7x to the fifth minus 11? Well, do we have to have every terms right in the middle? No, not at all, right? Again, we have nice number, variable, exponent, and number term only. So this is polynomial. Now another example would be 5x to the square. Well, isn't that monomial? Well, yes it is. It's a single term. But every monomial also considered as polynomial. So I guess if this is like polynomial, right? Then I mean, and it includes mono. It includes the monomial. So every monomial is considered as polynomial. So in that same sense, let's say if you have another example, let's say 4, a single number only, that's monomial term. Remember back in the examples of monomial, a single number was monomial term. So again, single number considered as polynomial as well. Okay, now let's talk about examples of non-polynomial. Oops. Non-polynomial. So what we really should look for is that exponent of the variable, right? So for example, let's say we have just fine looking mass expression, um, but let's say one of those exponent is say -2, something like that. These are all fine except this, and that's a trouble point. Because of that one negative right there, this whole thing become non-polynomial, right? Another possible example, -4 x to the third plus 2x squared minus 3x to the 1/2 plus 11. All right. Again, everything else is just fine, except for what? Well, you guessed it right, except that -1/2. This is non-integer, right? What about this? Negative integer. Negative integer or non-integer, they are all out, which makes this as non-polynomial, which makes this as a non-polynomial. Okay? All right. When I was learning this, teachers and professors making big deal out of whether this is polynomial equation or non-polynomial equation, but they didn't really explain why they are making such a big deal out of this. And much later that I found that if it's a polynomial, then it becomes smooth continuous curve. Smooth continuous curve. What do I mean by that? Let's say I have these, let's say I have these two graphs. I'm going to draw two graphs. Another one, not really straight. A little better. All right, so this graph, say, looks like this. And another graph looks like this. Now, if one of those graphs describe your bank account, right, which one would you prefer? Of course, this one, right? It shows all the move. It shows the trend and it shows everything, and everything can be explained. What about this? It was going up fine, but without any warning, it just started to go down. And it was going down. I didn't make any deposit. It went up. Could be a good thing. Well, it's going up and down. It was all up here. I didn't spend the money, but it went down like that and continue to go down. All those unexplained points. All this could happen because this is non-polynomial equation. So this is non-polynomial. And this is, of course, polynomial. So that's why all those mathematicians, if they have a choice, they rather work with polynomial, nice, well-behaving equation, rather than non-polynomial. Could be, trouble type of equation. That's why they prefer a polynomial, and that's why they are making big deal out of identifying what's polynomial, what's really not polynomial, and all the other things. All right. Okay.